All right, so we left off last time. All about figuring out velocity and accelerations for rigid bodies. So today and then next week, we'll still be working on kind of these topics. So today we'll almost step back a little bit and we'll just look at velocity analysis for rigid bodies and kind of systems of rigid bodies or mechanisms that are linked together. Next time we get together, we'll work on a special case of that, and then we'll talk accelerations, and then we'll be on to bigger and better things. But that'll take us just about up to Thanksgiving, which is amazing. So those of you guys planning your holiday travel already, we're not going to do discussion Thanksgiving week, so you'll be in here with me Tuesday. I know you'll be here because you won't want to miss this. And then, I don't care if you skip class on Wednesday, because we're not doing it. Okay. Yeah.
Will there still be discussion problems?
Will there still be discussion problems? There might be something on there. I got to check. But for Chapter 7, which is what we'll be starting, the things that we'll talk about kind of all build on one another, so it'll work out. All right, so today, what are we doing? We're doing kind of these first two things. Oh. Come on now, I turned you into a marker. There we go. So, velocity analysis. We're going to teach you three tools for doing this. And the one you kind of already know. So we're just going to put it to use for things linked together. And that's what we're going to call the vector approach. This vector approach is really handy for looking at a system of linkages and maybe for a moment in time saying, hey, what's the velocity here? What's the acceleration at this point? Number two, the differentiation of geometric constraints. You might have something that's linked up where you can look at it and say, hey, I think its x position is changing as a function of angle theta. Like, hey, if you can write that, well, you can take two derivatives, get from position to acceleration. So that's the kind of stuff we'll work on. Instantaneous center is a special case of number one, so we're not going to worry about that one until next week. So actually, I forgot there was something I didn't finish up last time. I didn't get the gears. I did post the example problems on the course page, and I won't do those, but I at least want to talk us through what's going on here. So in the notes, I think it looks like this. There's a little meshing point A. So I've got gear B spinning one way, gear C spinning another way. Maybe that's the first thing we should note right away is that, hey, if I got two gears connecting to each other, these are my gear fingers, I just kind of go like this, hey, these gears got to rotate in opposite directions. So little intuition for your engineering brain, hey, if this one's spinning counterclockwise, then this one's spinning clockwise because they're attached. And you could just kind of keep drawing them if you wanted. Always alternating. But we're going to just look at these two for now. So what we want to do is we want to be able to relate the angular velocity of one gear with the angular velocity of the gear that's attached to. So, this is how bicycles work. Hey, I'm spinning my front chain ring at one rotational rate, and I want that back wheel doing something different. So, it's set up like this, except instead of the teeth meshing, there's a chain. But we can talk about that. So if I've got this one rotating at omega b, and I got this one, little guy, rotating at omega c, we'll forget about those for now. What do we know? We know that this point where these gears mesh, they're stuck together, right? So at this point, they're traveling at the same velocity. And that's shared between both sides of those gear teeth. Because if one side was moving at a faster velocity than the other, you'd be shredding teeth off your gears. So They got to be moving together. That's that geometric compatibility that we talked about. So we can use essentially this vector method to try to describe how is omega c and omega b varying relative to one another. So let's work through this. I'll look at the B side and the C side over here. So for B, I can write out this velocity of A. Okay. The velocity of gear A, here we're going to assume B is pinned and C is pinned at the middle. And I might as well throw a coordinate system on here so it makes sense. X, Y, Z out of the board. So what do we know about the vector method? My velocity of A for this rigid body is going to be the velocity of B plus the angular velocity of the body, omega b, crossed with the vector between them from B to A. Okay? Do the same thing for C. Again, I'm writing the velocity of the A vector, though. So I've got the velocity of C plus the angular velocity of disk C, or gear C, crossed with this vector now, from C to A. Well, if these guys are pinned, B and C aren't going anywhere, right? Omega b, the way I've got this written, I've got my velocity of A. That's negative, so I'll say negative omega b in the k direction, crossed with, from B to A, I'm just going to call that r sub b, the radius of gear B, and that's in the positive I direction. I, J, K. So looking at this cross product, minus k direction, crossed with positive I. So I point down in the minus k, I cross towards minus I, and I get something in the minus j direction. Minus omega b r sub b in the j. That fits the picture I have, right? This is going down in the j direction. Hopefully our intuition could tell us that if this gear was spinning this way, at this point we're going down. Do that same thing one more time, but on the other side. Now, omega c, I've got this drawn in the positive k direction. So that's omega c in the k, crossed with my vector from C to A. That's minus RC in the I direction, because it's going now to the minus I. This cross product, k cross minus I, again minus j. Minus omega c RC in the j. We've got a pair of expressions, both for the velocity at point A. Put those together. We're left with minus omega b RB is equal to minus omega c RC. These are both in the j direction, if you care about that. So we get rid of those minus signs. And I can say that omega b is equal to RC over RB omega c. We just have a nice way to relate now the angular velocity of one body with respect to the angular velocity of its adjacent gear, if these are connected that way. And all it is, linear, a ratio of the radii. Maybe another day we'll say, hey, you know what? Maybe you don't have a ratio of the radii, but maybe you have a ratio of the gear teeth. Same thing. We could say that omega b is equal to the number of teeth on C over the number of teeth on B times omega c. The idea being, hey, these gear teeth have to have the same geometry to match up. And how is that circumference related? 2 pi r. So it's linearly related to r. I could use the number of teeth or the radii, depending on what I have. So this is pretty important for a lot of the things that we're going to do here. If you're a bicycle guy, here's my pedals in the front, but now I got a chain, right? Connecting these things. The story's still the same. If this is A and this is B, but now omega A and omega B certainly going to go in the same direction, and your shared velocity point that you need to think about is your chain. So whatever's happening here, velocity of P, I guess. That's point P now. That chain is moving, and it's purely translating. So this is also that same velocity of P. So you can play that exact same game we just did with the gears, except now instead of having the mesh point between the gears, that connection point is at the top of your chain. But this is why you change your gears in the back, changing the torque to make it easier to pedal up the hill, and changing your ratio to little gear in the back, big gear in the front when you want to go super fast down a hill or on a straightaway. All right, that's the thing I want to talk about for gears. Again, the example problems from that are posted on the class webpage. These first couple slides are just going to be on vector analysis. And, it's pretty much what we just did, right? If I take a jump back here for my gears, we did a vector analysis that describes how is one point of that rigid body moving with relation to another point that is attached to that same rigid body. So for these gears, we said, hey, how is point A moving if I know how point B is moving and I know that angular velocity? Okay. That's what we can do. We can step to any old points on these rigid bodies. And that's the equation we used. So that's all old news. But now, how are we going to use this when we start putting things together? And before we start putting it together, we'll do an example. Here's just a couple tips to make your life a little bit easier. So here I had some disks that were rotating, and I called them omega A and omega B. But sometimes you're not going to have a disk, you're going to have a link, a bar. And that's going to be connected to another bar, which is then going to be connected to a disk. I don't know if this thing actually would move anywhere, so don't worry about that. So if you have these various points, like, hey, figure out what's happening. Maybe we're comfortable calling this disk, it's rotating about point D, omega D. But these guys, you don't want to go in here and say this one, hey, this one's rotating at omega B because B is on there. Do yourself a little favor when you're writing out the angular velocity of bars. Name them with both their endpoints, omega A and B. This one, omega BC. Because now, like in your head now, hey, it's attached to two pieces. But by writing this out to me, I also think that, hey, point B is on this rigid body. Point B is also on this rigid body. This point B is going to be very important to us being able to solve what's happening in this mechanism. Because I know there's some compatibility here. B is stuck to both sides. So that velocity of B is shared between both these rigid bodies because that's where it's pinned together. That pin can only have one velocity, right? If the thing doesn't break. And that's really what point 2 is. We have these shared joints that have the same motion in the mechanism, and it's got to move a certain way. So when we're starting to look at these mechanism problems, we're always trying to gain a little bit of info. Hey, I know B is connected to these two pieces. Hey, let's for a second, I don't know. Well, I kind of screwed it up. I was going to add one more thing. Hey, maybe A is, I lied. A is on roller supports. It's no longer pinned. Maybe by peeking at this geometry, I can say, hey, that velocity of point A on roller supports, I know that it's something in the x direction, but it's 0 in the y direction. You were able to inspect from this geometry, the way it was set up, what other information can I glean just by looking at the way it's constructed? All right, last thing, 2D problems. That's what we're dealing with for all the mechanics. Our sign convention. If we're in a generic XY system, Z is out of the board, and a positive rotation about Z counterclockwise. So, counterclockwise, counterclockwise. I drew these both in the positive direction. Clockwise, that's the negative direction. Sometimes you're going to have a mechanism that's linked up. It's got a whole bunch of pieces. And your brain can't figure out, well, I don't know, just by looking at this, as this thing rotates, is omega BC, is it positive or negative? Like, I don't have any intuition on that. Who cares? Don't worry about it. Write it down in the positive sense. And when you go to do your vector equation, your vector stuff, you'll get omega BC, right? You'll just plug it in there. And you'll say that is equal to omega BC in the k direction. You're going to solve the problem through, and then you find out that omega BC is minus 2 radians per second. Who knows? Some number. But you're going to find out it's negative. All that means is that, hey, walk yourself back to the drawing. I drew everything positive. I entered all the equations using positive values. I got a negative result. I know that goes the other way. No big deal. All your math is still good. You just have a negative sign there. It's like when you draw free body diagrams, right? You draw all your forces like they're away from the body in tension. Sometimes they're negative. That means it's pushing on you. It's in compression. All your math is good. It's just how you've entered it into the equations. So sometimes it's going to be very easy to eyeball and say, yeah, this is rotating that way. Its buddy's rotating the same way. You're that clever, go for it. If you have that doubt in your mind, draw everything positive and let the math tell you otherwise. Okay? That's it. We're just going to crank some examples now. All right, so we've got block C is moving downward at 4 feet per second. Determine the angular velocity of bar AB at this instant shown. So if I've got to figure out something at the instant shown, I'm using the vector method because I think it's easy. If I got to figure out, hey, give me the angular velocity of bar AB as a function of our position here, our position Y. Well, maybe now I'm going to use a different approach that we'll talk about in a bit. But if I need an instant shown, vector approach is going to be the way I'm going. All right, so what do we know? We know the block is moving down, VC, at 4 feet per second. But we also know that it's got no motion in the x, right? That's what this little channel is trying to show us, is that we're not moving back and forth in x. We've got point A that's over here and pinned. at the angular velocity of bar AB. Hey, we're trying to find omega AB. Let's use the thing I just told you. Let's assume it's going in the positive direction. And if it's not, the math will tell us. Right? Write it in its positive sense. The other thing we've got going here, this point B. This point B is going to be shared between our two geometries, our two pieces, our two rigid bodies. So when I'm thinking about these problems, hey, I know something over here at C. That's the information I know to start with. I'm trying to figure out something way over on this other end at omega AB. Point B is that shared piece in the middle. So if I need to know point B is shared, I start from what I know and I work towards that shared point. So writing equations for the velocity of B is going to be how we tie together what these two bars are doing. So we're given the velocity of C is, I'll write it this way, 0 in the I direction minus 4 feet per second in the J. Right? That's all we know. We want to find omega AB. So let's start where we know things. Point B is shared. So point B being shared, we want to write expressions for point B. So from bar AB, we'll work to the right towards B. From point C, we'll work back to the left towards point B. So for bar AB, let's write our velocity of B. Our velocity of B is equal to the velocity of A plus the angular velocity of AB crossed with the vector from A to B. Right. That's our expression for rigid body velocity. Only valid if A and B are on the same piece. If A was over here, doesn't work anymore. They got to be on the same rigid body. Got to be shared. Okay? So velocity of A, pinned. That's 0. Velocity of B, I don't know. Omega AB, I'm going to call that omega AB in the K direction. I don't know if it's counterclockwise or clockwise. I'm just going to write it in as if it's in this drawing here, as if it is going counterclockwise. Crossed with my vector from A to B. That looks like 2 feet in the I direction, going this way. I, J, K coordinate system, K, crossed with I, I'm left with something in the J. So I've got 2 omega AB J. That's as good as I can do for now. Bar BC, I'm working back the other direction, but I'm using the same rigid body velocity expression. The velocity of B is equal to now the velocity of C plus the angular velocity of the rigid body, omega BC, crossed with the vector from C to B. Here we got a little more geometry. This vector from C to B is a little sneakier. 30 degrees, 3 feet. So RBC, I've got to come down in the Y and then back in the X. So this would be my y component, 3 sine 30. My x component, 3 cos 30. All right, so continuing this. Velocity of B. My velocity of C we were given. That's minus 4 feet per second, only in the y direction. Plus, my angular velocity of BC. I don't know which way it's rotating. I'm just going to go like this. Omega BC in the K. The math will tell us. Cross with my vector from C to B. That's what I've just drawn out. So it's minus 3 cos I, cos theta I, and minus 3 sine theta J. If you like doing your cross products, kind of old school, IJK, 0, 0, omega BC, minus 3 cos theta, minus 3 sine theta. Sorry, that's a little messy. And 0. My J term, I'm going to pick up 3 cos theta times omega. And then this guy with my I term, minus 3 sine theta omega. But it'll be a minus and a minus. So my velocity of B, minus 4 feet per second J, plus, what do I get from J? On J, I get down minus 3 cos theta omega BC. And then coming up the hill, I got a minus, so that's a plus 3 sine theta omega BC, and that would be my I direction. All right. So I got 2 guys that are buddies in J, one that's all by himself in I. But what do I have? I've got an expression for the velocity of B. I'll take you back in time 3 minutes. And I've got an expression for the velocity of B. This one just came from the other direction, though. This was my bar AB. This one was from my bar BC. That point is shared, so these guys are equal. So I can set one side equal to the other. I like to do this. Look at my I terms and my J terms separately. It's a little telling. So from the velocity of B from the A side in the I direction, goose egg, I got nothing. But velocity of B from the C side, I got a term. 3 sine theta omega BC. Theta is 30 degrees here. This is not 0. This tells me omega BC has to be 0. Next time we get together, you'll be doing that by inspection. That's what next class is all about. All right. But in the J term, I got 2 omega AB is equal to, now from the other side, minus 4 minus 3 cos theta omega BC, which we just said was 0. Omega AB is minus 2 radians per second. Hey, the way I drew it in our figure, the way I added it to all my equations, wrong. I don't care. I can write it. Omega AB, the vector, is minus 2 in the K. So, however you had it, if you go about doing it and you get the value 2 and you drew the arrow going the other way, nailed it. If I drew the arrow going my way and I got negative 2, nailed it. We both got it right. If I asked you for the vector, then only I got it right. I win. All right, so for these vector problems, these linkages that you see, there's a whole bunch of pieces. Like, don't get overwhelmed. Start where you know info. Work your way towards where you don't. And when you get stuck or stopped, start where you know some more info on the other side. And work your way together. Hopefully you'll have enough equations, unknowns, to be able to solve for things. Remember their vectors. So you got something happening in x, something happening in y. So you have two different sets that you can solve with. If you do get to a point where you're like, hey, I still can't solve this, maybe you look back and say, there's something about this diagram that I didn't get. Like maybe you didn't realize that there were walls here. This thing had to slide vertically. Right? So. Now the other thing we'll see here is that, hey, B is pinned to this circle. This thing is traveling in a circle. And at this point, horizontally, it was obviously going purely vertical. That's a thing that you can do also to make your life a little easier. Okay, so that's the vector approach where you've got links and you're setting up the velocity of one point with respect to another. You can do that for multiple bodies. Here's a different technique. This one is, I think, much more straightforward, but in practice, I feel it's harder to do. We call it the differentiation of geometric constraints. So if you've got a system where you can describe the motion of one variable with respect to another, if I can do that, and I can set up an expression to say how these two things relate, so in this figure here, I know how x and theta are related. I'm sliding this box over. And as I slide this box over, that arm rotates, right? So I know that my position of that box and my angle are related. If I can write that expression, hey, all I need to do is go to take time derivatives, to go from position, one time derivative gets me to velocity, next time derivative gets me to acceleration. That, like, the process sounds so easy. Like, yeah, of course I can do that. I can draw geometry and I can take derivatives. And then I'll show you this example that looks so simple, and the geometry is in the algebra and the calculus is a pain in the butt. But either way, this technique, super useful though, when you've got points that the geometry contacting, it's not like a rigid link where, hey, these guys are like stuck here, and wherever this guy moves, this guy moves. No, that contact point between these two bodies changes. So I can't really get away with that vector method because this point P at some time is going to be here, and at some other time it's going to be way up here. So we're not quite so lucky. The other thing is, with the differentiation of these constraints, is that you can get your velocities and your accelerations, your angular velocities and the angular accelerations as a function of time, and not just an instant in time. Like, hey, that previous picture, what we solved for was only good for that specific moment in time. As soon as that slider went down further, that angular velocity was going to change a little. And when it started coming back up, it was going to change a little more. So this, you can write an expression for x and theta, and then you say, hey, for any position x, I know what omega is. I know what alpha is. And that's what we're going to try to do. We're going to try to write omega and alpha as a function, actually, as a function of their angle. That's what the question says. So, as a function of angle theta, we want omega of theta and alpha of theta. So, looking at this thing, we say, hey, theta looks to be a function of x, right? As I change my x position, theta changes. Can I write out what that theta might look like? Well, as this box slides over, this bar goes up. So they're related by some trigonometry. Here, the easiest thing for me, this contact point changes, so the hypotenuse is always going to be a different length. But if I look at tangent of theta, h over x. That's the hard, well, that's the easiest part. This one is goofy in that the calculus is weird. A little, not weird, but that you got to think about derivatives of tangent, which we don't think about every day. So, but this is the heart and soul of the problem. I've related some variables. Now we can start taking some time derivatives and see what happens. The one thing we're told also is that the velocity 0 of that thing is constant. And it's moving to our left. So our box is sliding to the left. All right. I'm going to rearrange this to make it a tiny bit easier. X is equal to h over tangent theta, or h tan theta to the minus 1. I got this expression. I want to start taking some derivatives with respect to time. So the derivative with respect to time of x dot, or velocity. H, that's a constant. Derivative of this monster, I got minus 1 comes out the front. I'll put that in front of h. Then I've got tangent theta. This goes to 1 less, so minus 1 becomes a minus 2. And now I need to take the derivative of what's inside this power. So the derivative of tangent theta with respect to time, derivative of tangent is, yeah, someone knows, secant squared theta, showing off the calculus. And then derivative of theta with respect to time, d theta dt. Ah, that's a t. So this is also theta dot, or omega. However you want to do it, right? So my x dot here, that goes to v0 in the minus direction, so put minus v0 there if we'd like. Minus signs will then cancel. v0 is equal to h. Tangent squared, but negative, so it's in the denominator. Tangent is sine over cosine. So if it's in the denominator, I got to flip it sine squared over cosine squared. So all I've done is kind of snuck this back to the denominator, squared it, and then flip things around. Secant squared. Secant is 1 over cosine. So our cosines will cancel. And this is our omega, or d theta dt. Rearranging, omega is equal to v0 divided by h times sine squared theta. Step 1 done. Give me the angular velocity as a function of angle theta. We're not done yet, though. We want to get to angular acceleration. Now we take this derivative with respect to time. We know that this is the time derivative of angular velocity. So I take the time derivative of both sides. My omega goes to alpha. And we start working on this. v0, that's my velocity. It was a constant, so v0 over h is a constant we can pull out. Derivative of sine squared. What is this? So I bring the 2 down, 2 sine theta. to the first power now. Maybe you can do that if you like doing that. And then the derivative of sine theta with respect to time, derivative of sine is cosine theta d theta dt, or theta dot, or omega. So alpha is equal to v0 over h, or actually 2v0 over h, sine theta, cosine theta, omega. Close. Alpha as a function of theta. I got an omega in there, but we've got omega. We just solve for that. v0 over h sine squared theta. So alpha is 2 v0 squared over h squared sine cubed theta cos theta. Obviously. Pretty simple to relate x and theta. Kind of a bear to do the rest of the calculus. But we get something nice in the end. I've got an expression for angular velocity as a function of theta. And essentially that's a function of position, right? Because theta and x are related. Got angular acceleration throughout all angles theta. You can put in any old angle you want, as long as it works with this geometry. And you'll get the answer. So it's pretty handy. All right, one more problem. I've got an off-center circular arm rotating about a fixed point O. Point O, fixed. Not at the center, though. And it's driving plate C. Hey, you car guys know. It's like how cams work, right? Camshafts and lifters and valves and all that stuff. So at the instant theta equals 30 degrees, the cam is rotating about point O with an angular velocity 4 radians per second and an angular acceleration of 2 radians per second squared. We're going to assume positive counterclockwise. For 1 point, write an expression for position x of c of the plate as a function of r, little r, big R, radius, and theta. Okay? What the heck is x of c? X of c is the position from my pin in the x direction to the contact point, where we're hitting that, that lifter. For a bonus point, differentiate twice to get the acceleration of point C. All right. So we're pinned over here in the corner. Here is the actual center of our disk, not pinned, because this whole thing, now this center point, if you wanted to think about it, is riding a circular path. Here's our plate C that slides back and forth, depending on where this guy is in position. We've got our angle theta defined. If I drew a line from O to the center, this angle is theta. The radius of this circular thing, that's what we're calling big R. Big R is 150 millimeters. Omega is 4 radians per second. Alpha is 2 radians per second squared. And I'm given some initial value of theta. Little r, the position from O to the center, I've got that as 120 millimeters. All right. Our goal, write x of c as a function of theta, r, and big R. It told us to do that, so we're going to do it. But It's exactly what we just did for the last one, right? I had some geometry. I had two position variables that I could relate together, x and theta. It's exactly what we just did. I got theta here, and I've got this x position. Now, this is the variable that we're trying to track from here all the way over to the plate, x sub c. So from this drawing, it's kind of easy. We can just use some geometry to pull that off. X of c, kind of two pieces. First, I've got big R, easy. And then I've got this little leg from the rotation. And for us, if that's angle theta, that's 120. This would be my sine leg. Little r, sine theta. So maybe to help you think about, well, what does this thing look like? This would be my theta equals 0. Straight down, right? To my center of gravity from point O. That vector that I'm measuring, sine of 0, xc is just r. Check. That makes sense. What about 90? This is my point O now. So this is r, this is little r. Sine of 90 is 1. X of c is r plus little r. R plus little r, xc. Okay. You write something out like this, draw yourself one picture, two pictures. That's probably all you need to convince yourself, yeah, I nailed it. Or, right away. Maybe I got a sign here, or maybe something doesn't work. But that's what we have. So we just got 1 point. 2 points differentiate twice with respect to time. Time derivative of x is my velocity, or x dot of c, whatever you want to call it. And we look at what we're derivative of big R. That's just the radius of that thing. That's staying constant. Little r, also a constant, and I got a sine theta. So this goes to r. Derivative of sine is cosine. But I'm doing this with respect to time. So the derivative of cosine theta, theta dot. One more derivative. I get to the acceleration of c. That's x double dot of c. Now I've got two things that are a function of time, both theta and theta dot. So I've got to do product rule. So the first one, derivative of the first, derivative of cosine theta, got minus r sine theta, theta dot, times the second, theta dot, plus the derivative of the second times the first, r cos theta times theta double dot. Minus r theta dot squared sine theta plus r theta double dot cos theta. One minute left. You can plug in. Theta is 30. Theta dot, 4. Theta double dot, 2. And you get an answer. Minus 752 millimeters per second squared. All right. That is all for this. Next time we get together, we'll do a special case of vectors that will confuse you but make your life a little easier.